Antarctica is changing very rapidly. What we're trying to do is understand how these cracks grow and predict the timing of these big calving events that create very large icebergs.
We don't know what controls when they break off and how they break off.
We don't really understand how much sea level rise is going to be caused by ice shelves. We collect a lot of ice cores, we break it, we see how tough it is compared to other ice.
There isn't much data on that because getting access to ice from Antarctica is difficult and you have to get it halfway across the world without melting it.
Ice shelves are very important on the global scale. They are the floating parts that surrounds the margins of the continent. They hold back ice from the interior of the Antarctic continent. There's been periods where we've had sudden ice shelf collapse or loss of ice shelves. The famous one is Larsen B in the early 2000s.
We had extreme warm temperatures one year. We got a lot of melting on the surface and then a lot of fracturing, and then that ice shelf completely disappeared. It just disintegrated really rapidly. And that means that this ice that's flowing off of the continent has nothing stopping it. So that ice can just completely flow out into the sea and it breaks up as icebergs and then just contributes to sea level rise.
Antarctica contains the biggest ice sheet in the world. It has the potential to raise sea levels by tens of meters. And we are starting to see significant contributions to sea level rise from loss of ice from Antarctica. A lot of the world's population live in coastal cities and around coasts, and so this will quickly have a direct impact on coastal ecosystems, mass migration, and for society as a whole. So Antarctica loses about half of its mass through iceberg production, through calving.
That's a very natural process, and we expect that to happen nicely, continuously. The ice shelf grows, it breaks off, continues to grow again. But we're seeing that this process is actually being changed by the climate, and we want to understand what's happening there.
The big changes that have been happening are mostly in West Antarctica, so areas like Thwaites and Pine Island. The ocean is warming and a lot of the ice shelves are melting and thinning, and that is reducing their buttressing power. The effect of calving is less well understood. I work on the Brunt Ice Shelf, where we have the Halley Research Station. We are interested in the different drivers of crack growth. So this particular ice shelf has a number of active cracks within it. So it's a dynamic ice shelf. It moves about 4 meters a day, which is relatively fast. But also it's had these what we call rifts, which is a full thickness crack that goes right through the ice shelf, and have led to several large calving events in the last 4 years.
The Rift Tip project is about trying to understand the rate and timing of why ice fractures and why we get these large icebergs produced from ice shelves. Iceberg A81 was formed from Chasm 1. Chasm 1 was this large rift that we expected to form at some point. The ice shelf had got as big as we knew it had got before, and then that crack eventually propagated through the ice shelf, and then the iceberg broke off. The other crack was aptly named Halloween crack because it was found on Halloween. And this grew really quickly and it was less expected and led to us realizing that maybe the way this process happened, we don't understand as well as we should. So if we can't understand how and when ice fractures and produces icebergs, we don't really understand how much sea level rise is going to be caused by ice shelves. The first time I saw Halloween crack, we were flying towards Halley Station out of the little twin otter plane, and you see this large opening and you just go, wow, it's huge. It's open water, this vast expanse that if you were on one side of it, you could be convinced that maybe it's just sea and that there's not ice on the other side of it. But as you fly over the crack, the further and further you get towards the tip of it, it just gets narrower and narrower. And then we landed in the plane to do some surveys around the very tip of Halloween crack. And All that remained was this very, very tiny hairline little fracture in the surface of the snow, and myself and the field guide were walking along tied up with a bamboo stick trying to find where this crack was. And that's in sort of 50 kilometers that the crack has gone from this massive, massive thing to just this tiny little hairline fracture that you can hardly even see.
What the whole project is designed to do is fill in the gaps between understanding what's happening at a small scale with crack growth and the large scale with iceberg production.
We think it all comes down to sort of centimetre, millimetre ice crystal scale of where that crack goes. It's such a small process that we're trying to understand with all this large equipment and these large expeditions.
The main thing that we're doing here is joining all these things together on a specific crack, on a specific ice shelf, and so we're getting a full view of everything from the micro scale to the wider impact on the actual iceberg formation. Our research station Halley is down here. The area we've been working in 24-25 season is up here at the tip of Halloween Crack. So this is about a 50-kilometer drive. The crack has been growing since 2013. We've been monitoring its width very closely. We've been monitoring strain rates around the tip of that crack. And more recently, we've set up seismometers around that crack. It is quite amazing what we can do with the satellite imagery these days to understand how cracks are growing, but it doesn't tell us about what's happening in the subsurface. For that, we've been using radar measurements, so driving a skidoo with a radar system towed behind, which can image the properties of the ice at depth. We can also use that to find cracks that are not necessarily visible at the surface.
In Antarctica, we actually see quite different characteristics of this fracturing, whether that's on the Brunt Ice Shelf, where I've been to, or Larsen Sea Ice Shelf, kind of tends to do the complete opposite of what we'd expect. We want to understand why it is that when ice fractures, it goes through certain types of ice more so than other types of ice. So I use geophysics to try do that. The previous season, I'd gone over to this bit of ice and installed 2 instruments that were there to track if the ice did break off. And then we turned up this year and they're just gone. The ice is gone, the instruments are gone, and you have this real understanding of the scale of what we're studying. We also collect lots of ice cores where we're really looking at the very small scale properties. So we drilled down to over 130 metres and we roughly recover a core every 80 to 90 centimetres.
When we're in the field and drilling the ice, it's quite a exciting process.
We need the cores to be in a real pristine condition. They can't have any fractures or anything in them that we've created. You obviously accidentally drop a couple and theoretically they're worth about £8,000 per metre is the price that BAS puts on them.
The ice has to be taken back to Halley. Then at the end of the season it was collected and then loaded onto the Sir David Attenborough ship.
It's a long process, so we had to wait around 9 months to see the ice again.
That's quite a nervous process when it arrives here. You want to make sure that it's still in the same shape that it was when we originally logged it.
The ice has just moved in a regular freezer van. Often the driver will ask us what we're transporting and is always quite excited when they hear that it's ice from Antarctica. Relief when you finally get your hands on them. You often get very friendly people wanting to help carry the boxes off of the lorry with no grace and decorum, and you're sat there thinking they've made it this far, not broken. Please, we don't want them broken. We pick and choose the cores that we want. We then use this scanner here where we're able to take a really high resolution photograph of the cores, and from that we can look at whether or not there's any ice or features in the core that we can't necessarily see with our eyes. And then we take the cores through to the other freezer where we cut and prep them, and that's where we do all our analysis. This is one of our really hard continental ice, bits of ice that is really uniform, like really uniform bubbles, really strong, really old. The smaller the bubbles, the older the ice tends to be. And that's why people use it for chemical analysis, because any sort of bubbles that are trapped inside it still preserve the conditions of the climate at the time that they were trapped. This one is around 128 meters deep from the ice shelf, and then as we melt it, we'll see what's going on inside the ice and the bubbles. We think from the size of the bubbles, it could be anything from sort of 100,000 years old to 500,000 years old, which for ice is not that old. This ice was formed somewhere way inland on the continent of Antarctica and has then eventually flown off into the ice shelf. So if you melt this ice, you'll hear it bubbling. As the little bubbles inside, the change in air pressure, they release. We melt it in the freezer, and as we're melting it, we're able to extract the gases off of the core, and we're also able to keep the liquids. We can look at different types of chemistry that could be to do with the amount of sea ice that was present in Antarctica at that time of year. It could be to do with volcanic activity, and we use all that to both understand the chemistry of the climate in the past, but also age our ice. So without that, we haven't really got a good understanding of how old the ice is that we're studying.
What we don't really have at the British Antarctic Survey is a capability to do physical property analysis of ice.
The BAS team reached out to us with our long-standing history of working on ice. I'm particularly interested in how geomaterials deform full stop, and understanding ice is a very similar problem to rocks, just under different conditions and different style. Well, we have 5 ice labs. We have a lot of equipment built by our excellent engineers here at UCL, and we can squash things, and I'm excited to squash anything. You give it to me and we'll squash it. Here the problem is coming up with some experiments where you can actually measure in a controlled environment the strength of ice in the context of the ice shelf that they're working on. If you have a large fracture that goes from top to bottom of the ice sheet, you're going through this material. Just like if you're tearing a piece of paper or tearing a piece of card, you need to know if you're tearing card or paper, because one's going to be easier than the other, and that will control where the fracture goes. The idea here was to actually get core and actually bring it here and test that under some very controlled temperature conditions, controlled rates and speeds. How does the ice fracture as a function of depth? Well, it's pretty exciting, you know, having a freezer full of ice that has come from Antarctica. Significant amount of field work has gone on and logistics to get it from where it was drilled to bring it here. I certainly lose sleep on whether this stuff will melt, that's for sure. I wake up in a hot sweat. What controls the strength of a material is the things that are within it. So many things that are crystalline essentially have a grain size, and the grain size is a primary control on how things break. On ice, we have to look at that under the microscope because these grains are really small. And to do that, we make a thin section.
We essentially take a really thin piece of ice, glue it to a piece of glass using just cold water, and then file it down until it's 1 grain thick. And then we can use polarized light to see the orientation of the crystals, the size of the crystals, and that tells us about whether or not there's been any sort of stress on the ice that could have made those crystals grow in a certain direction, whether or not the fracture has maybe pushed the crystals into a sort of direction. It also tells us maybe about how long the ice took to grow, if it's melt, if it's fresh snow, if it's old. So we can learn quite a lot from the crystal structure. This is ice from quite shallow on the ice shelf, maybe around like 15 meters. And it's got this really, really clear ice that would have been formed when there was melt at the surface, and it's percolated into the ice shelf and then refrozen at a later date. So we're gonna look at what's inside it. So this is just a light board, and this is just polarized paper. When we look at the sample at the moment, it just looks like regular ice. This is our melt, and this is our firn, our shallow snow. And then when we put the polarized paper on, we can really clearly see the crystals.
So our melt has really quite big crystals, these bits here. And then the fern in between, this like almost snow transitioning into ice, doesn't really have large crystals at the moment. It's pretty fresh, pretty shallow, pretty new. Hasn't had time to grow into any sort of large crystal at the moment. This is one of our samples from a little bit deeper down where we've got our fern and then our melt.
It's really nice.
It looks like magic, doesn't it?
And that's very useful because it allows us to tell us things about the orientation of the crystals and how they were formed. And if, for example, they were stressed, also the changes in colours would be representative of that as well.
Because we see completely different colours, it actually means that there's probably been no stress acted on it, that all the grains are completely randomly orientated. If they were all pink or all green, then they'd all be facing the same direction, which means that something has made them form in that way or made them move in that way.
Random scattering of crystals is actually the most common thing. So that's what we'd expect it to look like. If there had been some sort of structure in the ice, then we would think that there's some sort of stress acting on the ice shelf to push the crystals into a certain orientation, or it's that the fracture, the tip of the fracture, is actually causing the crystals to change orientation.
What we then do is test how does the ice fracture as a function of depth under some very controlled temperature conditions, controlled rates and speeds. We have to prepare samples, shot the core up to make semicircles. So what we've got here is a hydraulic press, and I can put about 1 ton of load maximum on a sample. We're not going to need to use anywhere near that for the ice. It's much weaker. But it's been custom designed and assembly to essentially load our sample. There's 2 rollers here and here, and then we'll slowly increase at a control rate, the piston coming down, and it will increase the stress until it breaks. In here is a load cell. This measures and sends a signal back to the computer telling us exactly what the load is. What we've also got is a high-speed camera that's set to record at about 18,000 frames per second. That should show us the fracture propagating. You can see here the sample, zoom in. We're going to load this down. It's going to come down. What we're hopefully going to see is that fracture propagate across. 0.01 millimeters per second is what we're going to bring that down at. Consistently starts.
Ready? Start experiment.
This is the distance going down, so that's 18.7 millimeters. You see we're now at 18.5 millimeters, so let's move 0.2 of a millimeter. So we're waiting for essentially a kick in the stress. There we go. And we're starting to load the sample now. It's going up nicely. Oh, no. Increasing stress. Beautiful signal there. Great. That was a really nice one.
So this is the fractured surface of the ice that we've just broken through. So we'll measure the length of that edge and then use that to calculate the fracture toughness.
So this is the background levels where there was no load on the sample. And as the piston came down, you can see that there's a load being increased. It's non-linear because ice has cracks in it. And you see a nice linear elastic phase here, and then you can see stress build up, and then you see there's a crack and there's a stress drop. But we've certainly, in previous cores that we've experimented on from this batch, we've had samples much weaker and samples much stronger, which clearly relate to the microstructures. And what you can see is that the fracture's there. If I go forward 1 frame, the fracture's here. So it's moved from here, which is about 1 centimeter, and on the next frame, it's moved from there. So it's moved about 1 centimeter in 1/18,000th of a second. You're talking about rupture tip speeds there of approaching 1 kilometer per second, so really fast. We're actually finding that the weak fern snow is surprisingly stronger than previously thought. Lots of assumptions in the literature that this stuff is actually quite weak. We're actually seeing that the shallow snow is actually a lot stronger. In particular, we're finding these melt layers are much stronger. Nobody has measured that, to my knowledge, the strength of these layers so far. So there's clearly different aspects of the ice structure, some things that we know and some things that are completely new in terms of variations of strength. We are systematically going down through all of the ice, measuring a variety of different parameters, which is really going to help us in terms of feeding that into the larger scale models.
We're essentially getting the missing pieces of the puzzle to understand what's quite a complicated dynamic evolution of the ice shelf over the last 10 years. This is some kind of example of our model output. This is in just a two-dimensional form of the front of an ice shelf, where the colours represent the stress with depth, and this dark area is a representation of an area where a crack has appeared. This shows how over time the crack evolves and the stress near the crack tip evolves, and once it exceeds a certain threshold, the crack can penetrate all the way through the ice and the calving event happens. And so what we can see with our new model is a time scale for when a new ice front appears, how long it takes to create enough stress that will create a new crack and another calving event. So that's kind of an exciting point that we've got to with the model so far. We can run the model forward in a kind of predictive way and find out what the future behaviour of this particular ice shelf will be. Somewhere like Thwaites Glacier, where we're seeing some of the biggest impacts of climate change, the cracks in that area are less well understood and it's much more difficult to work there. It's harder to access and it's more dangerous because the ice is moving more quickly. The work we're doing and the models that we're producing will be applicable to areas like Thwaites and the rest of the Antarctic margin.
We need to do this research. We have to go to Antarctica and collect this data and model Antarctica to be able to understand how it's changing and really reduce our uncertainty in how that's happening, to have an impact and make a change.
We want to give policymakers the information that they need. To some extent, it's frustrating that not enough is being done about it from the policy side. I do feel like doing the science is important, and there's a range of sea level rise, but it's all higher than it currently is. We need to be as certain about numbers that we're providing, such that there's no excuse not to do anything, because this is very certain. We can tell you with confidence that this is how things are going to go.
To me, this is my first entry into an area where I feel I can genuinely provide some expertise that will help to something that is really important, fundamentally important for the future of humans on the Earth. And if I can provide laboratory data easily that will help researchers, then that's as exciting as it gets.
It's like nowhere else you will ever go, and you're there and it's so quiet and so beautiful, and the sky is so blue often. It's like a real blue that you don't get to see anywhere else, and it's just, really magical.
You would think that the excitement of going would fade over time, but for me it doesn't really. It's a beautiful place, and it's a shame to see it changing so quickly.